Hello, physics students. So this is mastering problem 6.72. This one is about a rock being dropped on the surface of a comet. And my drawing is comical here because it's totally not to scale, but the big lump that looks like a potato is the comet, and it has a mass of like 10 to the 13th kilograms, and the radius of it is 1,600 meters. They probably gave you that in kilometers, but you need it in meters for the universal gravitational equation, which we'll use in a moment. Now, here's the deal. If this was on Earth, this would be easy enough for us to figure out. The question was, and I need to go back and look because I don't remember how long. So we're looking for time for the rock to hit the ground if it's dropped from 0.6 meters above the surface of the comet. Now, I'm going to guess it's a lot of time because this comet probably doesn't have a very strong gravitational acceleration at all, but we're going to find that out. Now, this would be an easy enough problem. Imagine we're back in Unit 1 in kinematics, and we're like, okay, so it's 0.6 meters. I want to know how long it takes. So I'd be like, yeah, let's do this. Equals xi plus v t plus 1/2 at squared. And if it was on Earth, we'd just plug in negative 9.8 as our acceleration and solve for stuff. Now we're dropping it from rest, so that's going to mean this term is 0. I'm going to make, I'll make the xi 0.6. And xf I'll make 0 because it'll hit the ground, so 0 equals 0.6 meters. 1/2 negative a t squared. Now, here's the deal. We need to know the acceleration due to gravity on the surface of this comet. So that's where the real sticking point for this particular problem is. Now, let's see if we can figure that out. So on the surface of an object, big or small, whatever, what we can do here is we can say, okay, so there's gravity on the surface of the Earth, or the surface of the comet, and there's two ways we can calculate that gravity. One is with Newton's law of universal gravitation, and the other is with mg. So what I'm going to do here is I'm going to put Newton's law of universal gravitation and do the big G, big mass, little mass over r squared, and that equals mg. And the helpful thing here is that the mass of the little object cancels out, and that gives us a way to calculate the gravitational field of the thing. This case, it's a comet, and that gravitational acceleration is going to be what I'm going to use as my acceleration up here. So let's plug that in. 6.67 times 10 to the negative 11th. That thing has some units somewhere. I wish I could remember the units of that. So it's meters cubed over kilograms times second squared. And the mass of the thing is 1.0 times 10 to the 13th kilograms. That is not 31, 13. And the radius is going to be 1,600 meters, or whatever variety of that mass string happens to give you. N squared, because we want to get the answer right as opposed to getting it wrong. So give me a second, I'll go over to Desmos and figure out what that is. So I get the itsy bitsy teeny tiny value of 0.00260 and some change for the acceleration here. Meters squared, kilograms cancel. Yeah, it does leave you meters per second squared, doesn't it? It's crazy. It actually works. Now I'm going to come up here and continue on the journey here. So this is going to be 0.6 equals 1/2 times, oh Lord, I don't want to plug that number in just yet. I'm going to just take I moved the thing over. It was negative. This is negative. The negatives cancel out. AT squared, and then I'm going to divide both sides by 1/2 A. Okay, when you divide 0.6 by 1/2, you get 1.2 divided by a. We're going to square root it, so we'll get that equal to t. And then t equals 1.2, don't forget the square root, over the acceleration of 0.000265. All right, let's see what that comes out to, if it's anywhere close to what mastering says it should be. So I kind of forgot to click record before I wrote the answer down, but that gives me 67.9 seconds. That would definitely be an environment you would not want to sneeze, because you might actually accidentally launch yourself into orbit if you were an astronaut trying to walk around on that thing. That would not be an advisable extravehicular activity. But anyways, that's close enough. The one I see on my side of mastering says that it should be 88 seconds if it's dropped from 1 meter high. So that seems reasonable, that would be the that was a valid approach to this. That is a 7, by the way. There you go. Anyways, your version will be different. You'll probably be dropping from a different height or something like that. So hope that helps. Have a good time with that problem.